introduce it all this while because it is a little abstract and it sort of takes the focus away from the concrete things that we can do with matrices, etc. Even when one is doing linear algebra, but at the same time, but now that we've seen groups and quotients, I think it is we can conclude this course by looking at quotient spaces, vector spaces. I mean, there are later you will also see in topology you'll also see quotient topological spaces. So I just want to clarify that we're discussing quotients of vector spaces. So I mean, F is some field. I mean, for the purpose, you can just think of it as Q or R or C. Okay? But any other field is also okay. It is just and V a vector space over F. I mean F. Okay. So that's the that is what the okay. And W subspace of V. So now, exactly as we did for subgroups of a group, okay, we will define an equivalence relation, etc. Look at equivalence classes, and then observe that there is a natural vector space structure on the set of equivalence classes. Okay? Okay. So define an equivalence relation on V by setting V1 is equivalent, V1 is related to V2 if V1 minus V2 is inside W. Okay, so we have only defined a relation. The claim is that this is an equivalence relation. Okay. So let me observe that. So we need to check three properties: reflexive, this related V1. I mean, this is for all V1 inside V. V1 is related to V1. Since V1 minus V1 is 0, that is inside any subspace. Symmetric. Okay. For all V1, V2 inside V, if V1 is related to V2, then V2 is since V1 V2 minus V1. That's what we need to check whether that is inside. The first one minus the second one is inside W. That's what we have defined. Let's check that thing. V2 minus V1. But this is this is a vector inside V. It is negative of the vector V2 minus V1 minus V2. Okay. And V1 minus V2 is inside W, and W is a subspace. So any scalar multiple is also inside W. Okay. So this is symmetric and transitive. Okay. For all V1, V2, V3 inside V, V1 related to V2 and V2 is related to V3, then V1 is related to V3. Since V1 minus V3, it can be written as V1 minus V2 plus V2 minus V3. And both of these are individually inside W, and W is a subspace, so the sum is also inside W. Okay. So this is inside W, this is inside W, therefore the sum is also inside W. Okay. So the two vectors are related to each other if their difference in the first minus the second is inside W, defines an equivalence relation on the set on the vector space V. So we proceed. I mean, philosophically, we proceed exactly as we did quotient groups. Okay. So there's a minor catch. If you took an arbitrary subgroup and looked at the set of cosets, it's not a group. Okay? We need a normal subgroup for it to work. But here, yes, I don't want to get into the those things here. That is sort of automatic, okay? And we will see because the addition operation. See this coset, like, okay, I mean, this equivalence relation is defined by taking the difference, okay? But addition, difference means v plus minus of v2, and addition is commutative, and uh, on the entire vector space V. It's like an abelian group. Okay, so that's the reason why it sort of works. So by definition, okay, sorry, maybe by V mod W, we mean the set of cosets, set of equivalence classes for this equivalence relation. Okay. So now we would, okay, so what we want to prove now is that V mod W is a vector space and natural map from V to V mod W, which an element vector V is sent to the equivalence class containing it. That is a linear transformation. So sort of exactly the way we work in groups. If H is a normal subgroup of a group G, then G mod H is naturally a group, and the surjective map from a group element going to the coset, which is the same thing as group element going to the equivalence class, okay, is a linear transformation. So this is what I claim. So, and then we will look at some examples. Proposition. Define scalar multiplication. Define vector addition. Okay, let me just call it addition. Say addition on, okay, maybe on V mod W as, okay, so maybe we need some notation also. Okay, notation. Okay. By V bar, we mean the equivalence class containing V. Okay, so for V inside V. Okay. For a vector V, little v, by V bar, we mean the equivalence class containing that vector. Okay. So it's actually a set. It's a subset of capital V, but we are not concerned about individual elements in it. So we just think of it as one thing. Okay. Definition. Let V1 and V2 be inside V and lambda be inside F. So we are defining vector addition and scalar multiplication. Okay, because we want to make V mod W into a vector space. Define, so this is a definition of the addition. V1 bar plus V2 bar to be the equivalence class of V1 plus V2. Okay, so this is a, okay, so this maybe we have done these things earlier. So let me emphasize this again. We are defining the addition in V mod W. Okay. Okay. And similarly, lambda V1 bar. So this we are defining. What do we mean by multiplying a coset by lambda? Well, define it to be the coset of lambda v1. So remember, the vector space V is something that's already given to us. We know, I mean, when you say it's given to us, it means that we know how to do scalar multiplication inside V. Okay? Now we are extending that thing to a new set V mod W and saying how should we do scalar multiplication there. Okay? So we play. Okay? So this is how we are going to do scalar multiplication. Okay? So now proposition. With these operations, okay, V mod W is a vector space over. Okay. So this I won't prove. I leave this checking to you because you have to check that these two operations satisfy the conditions required. Okay. Yeah, so maybe I should clarify what is the zero vector, okay, and what is the zero vector of V mod W is the equivalence class containing zero. Okay. And okay, so check this. So proof. This I leave as an exercise to so it will also tell give you practice on arguing about these equivalence relations, and similarly for the group case cosets. Okay, so proof I leave as an exercise. Okay. Now let us look at some examples, okay, and then so then I want I want to make some remarks as to why such a thing is really necessary. Okay, and I mean, such a definition is really necessary, and not things that we have already seen. We have seen subspaces, we have seen orthogonal complements, etc. Okay, why such a thing is definition is new. I mean, this new notion is necessary. Okay, and yeah, and then we will reprove one of the theorems that we proved earlier about diagonalizability. Okay? So that's the plan, and okay, so I think that is enough for a start to understand, to think about quotient spaces. Okay? I mean, okay. So let's look at some couple of examples. Okay. Let's take the simplest example. I mean, it's not the simplest. Let us take sort of the first non-trivial example. Well, okay. So let V be R2, and so this is example one, and W be the span of the vector 1, 0, which is, we can think of it as the x-axis. Okay. So so this is R2. And W is this. Okay. So now, what does V mod W look like? So the point was that we would associate. Okay, I mean, we would relate two vectors inside V if their difference lies in W. Okay. So then AB is related to CD. Okay. So these are elements of V. Okay. By definition, if and only if the difference, which is A minus C and B minus D, is inside W. That's the definition. But what does it mean to say that it is inside W? Well, the second coordinate should be 0, because this is a span of 1, 0, okay, which holds if and only if B minus D is 0. That is if and only if B equals D. Okay. So we are looking at some two vectors here. Their second coordinate must be equal. That's exactly when they are related. Okay. So then we can draw a few equivalence classes. So W itself is an equivalence class. Okay, so these are all various equivalence classes. Okay. So all horizontal lines, they are exactly the equivalence classes for this equivalence relation. Okay. So let's write that remark. Okay. Therefore, the equivalence classes for this relation are precisely the horizontal lines or in other words, lines that are parallel to W. So these are the equivalence classes. Okay. And given any equivalence class, so what is V mod W? Well, it is a collection of equivalence classes. So each of them, we can represent it by some vector. So V mod W, okay, this is a set of equivalence classes. Okay, for this equivalence relation. And to represent it, to represent an equivalence class, we have to just say one element in it and say all things that are equivalent to this one, all things that are related to this. Okay, that's all that we need to say. Okay. So this is so then so, okay, so there is no natural choice for representing the equivalence classes. We could, for convenience, pick elements on the y-axis. So it is it's purely for convenience. Okay. There is no, we could represent, okay, the equivalence classes by the vector on the y-axis I mean, we could represent each equivalence class okay, by the vector on the y-axis okay, contained in the class. Okay. It is easy to check that a single class can only contain exactly one element on the y-axis, because if there are two vectors on the y-axis belong to the same equivalence class, the difference must be horizontal, but then that means that the two vectors are the same. Okay. So note, okay, each equivalence class contains a unique vector on the y-axis. Okay. Once that point is fixed, everything that is parallel to parallel to the x-axis passing through that point on the y-axis is at equivalence. Okay. So this is the okay. So this is the picture. Again, this is just for convenience. Okay. Whether you choose an element on the y-axis or you choose some other element on the which is on the same parallel line, the calculations are all the same. I mean, okay, calculations may be a little simpler because if you choose a vector on the y-axis, one of the coordinates is 0. So that might simplify some actual calculations, but not anything conceptually. So this is so for we could do that. Okay. But just okay. But I just want to clarify one point, which is okay. So I'll clarify it afterwards. Okay, so let us we'll come back to this proposition. We'll add. I mean, you will revisit some abstract property, okay, and then we'll come back to this. So this is one example. Okay. So similarly, let us just take a minor modification of this thing. Okay. V again is R2, and W is the span of 1, 1. So this is the line this angle 45 degrees, passing through the origin with angle 45. So this is, sorry, I mean, it should be one line. Okay. So this is, and the equivalence classes are, so two vectors are equivalent if their difference lies in W, okay? Or in other words, the difference is a vector that points at either 45 degrees or opposite. Okay? I mean, so that's okay. So V for all V1, V2 inside V, V1 minus V2 belongs to W if and only if the vector V1 minus V2 is with respect to all. Okay. So yeah. Okay. So this is a form. Equivalence classes are the lines parallel to W. So again, same picture. I mean, same thing. And there are, I mean, I've only drawn some finitely many, but remember there are uncountably many. Okay. Here also we can choose from any equivalence class. We can choose one that represents that class. And for example, here also you can choose one from the y-axis. Any one of these parallel green lines will hit the y-axis at exactly at one point. So you can choose that as the vector which represents that class. Okay. So here too, again, for I mean, so what representative we would choose typically would depend on what calculations we have to do and what would be convenient. So okay. So for example, here too, we can choose. I mean, for each equivalence class, okay, we can choose the vector, the unique vector along the y-axis that belongs to the class. As its representative. Okay. So this is the okay. So just for let's look at similar examples. Okay. V equals R3, okay, and W is some line through the origin, 0. Then V mod W is the set of all lines parallel to, all lines in R3 parallel to W. Okay. So I mean the picture is essentially the same, except the difficulty of drawing it in 3D. Okay. So for example, let us say V equals R3 and W is the XY plane. Okay. Then the cosets are planes parallel to the XY plane, planes inside R3. this set parallel to xy plane. Okay, so you can just think of these as some layers that are just parallel to the given W. Okay? And this is exactly what the cosets look like. Okay, I mean they're not the coset sequence classes look like. Okay, so now let us make one analogous to what the picture in groups. Okay, let's make another observation. Okay. The surjective map from V to V mod W, in which a vector is taken to its coset, is a linear transformation. Okay. Let's call this thing pi. So given a group and a normal subgroup, we would have obtained a group homomorphism, surjective group homomorphism there. Here, the nature of the map is that it is a linear transformation, and that is the assertion that pi, this map which sends V to its equivalence class, is a linear transformation. Okay? So we need to check that if lambda is a scalar and V1 and V2 are vectors, pi of lambda V1 plus V2, please just hold for 2 minutes. So this is the usual. I mean, the philosophy is the same. Okay. So here's a proof. Okay. So let lambda be inside F, V1 and V2 be inside V. Okay. So we want to show that pi of lambda V1 plus V2. So this is a convenient way of just checking V1 minus V2 and lambda times, I mean, scalar multiplication and vector addition, and also inverses. All of them can be checked simultaneously by checking this, by appropriately choosing lambda V1 and V2. So this is equal to pi of lambda times pi of V1 plus pi of V2. This is what we need to check. Okay. If you check this for a map of vector spaces, then it means that that map is, I mean, for a map pi of vector spaces, then that means that that's a linear transformation. Okay. This may not be the definition that we have used earlier. You would have explicitly checked that the map respects sums, map respects linear, the scalar multiplication. Map takes 0 to 0, minus to minus, etc., etc. But all of that can be subsumed in just checking this. So we need to check this. But what is so pi of lambda V1 plus V2? This by definition is the equivalence class of lambda V1 plus V2. This is what by definition this is. Okay. But we have said that the definition of addition in the quotient space is that it is lambda V1 plus V2. So this means coset, maybe I'll just write these things along the side. This means coset of lambda V1 plus V2. Here it means coset of lambda v1, lambda v1, and is given to us. Okay. Just to repeat, the addition inside V is given to us. What we need to define is the addition inside V mod W, and that's okay. So this, and this is same thing as lambda times V1 bar plus V2 bar. Okay. So this again is scalar multiplication inside, again defined by us. And this is exactly what we wanted to say, lambda pi v1 plus pi v. Okay. So this is the, so this v mod w is, can be given in a natural way, a vector space structure. And moreover, once we give this thing, the map from v to v mod w, in which a vector is sent to the equivalence class containing it, is a linear transformation. So this is exactly analogous to the way we have worked with groups. Okay. So now I want to revisit those examples, and then why. So I just want to emphasize one difference, okay, between things that we have already done once in class, okay, and quotient spaces. Okay. So we said, okay, so back to, okay, so sort of word of caution or word of, okay. So in example one, okay, we said that we can represent v mod w by vectors on the y-axis. Okay. But v mod w is not the y-axis. Okay. I mean, the first, first reason for that is that there is no way we can naturally think of v mod w as a subspace of v, okay, as opposed to y-axis is a subspace of v. We will see. I will prove in a few minutes that dimension of v mod w is dimension of v minus dimension of w. That we will see in a minute. Okay. But so in this case, v mod w is one dimensional, and it can be represented by elements on the y-axis, but they are not the same. Okay. That's what I want. Okay. For one, v mod w is not a subset of v in any natural way. Okay. As, okay, but y-axis is. Okay. So that's, I mean, in a very in a very set theoretic way, we see that these are not the same vector spaces. Of course, they are both we will see that they are both one dimensional, therefore they are isomorphic. Okay. But they're not. That doesn't mean that they are the same vector space. Okay. There is no natural way we can make v mod w sit inside v, as we have done for, as we could do for y-axis. So that's one thing that we should keep in mind. Okay. Okay. So we'll see what is the natural context in which v mod w shows up. But it's not a subspace. Okay. So that's the first observation. Okay. The second thing that I want to sort of, so maybe this is word of caution one. Okay. Word of caution two. Okay. See, when we discussed inner product spaces or Euclidean spaces, because the examples that I discussed are all over R here, okay, now today. Okay. So you may think that why worry about this quotient space? We could take W perp. But for the same reason, W perp is not V mod W. They okay. So in the examples that we saw, that we took, I mean, all the examples that we considered today, okay, are Euclidean spaces. Right? It's just R2 or R3. Okay? So then we may ask, if V mod W is the same as W. I mean, I should not say word of caution 2. It is essentially word of caution 1 itself. Okay? Maybe I should not call it 2. Okay? I'll just. Okay? Because I mean, there is a natural way to think about something that is sort of complementary to uh, to uh, to V to W. Okay? W perp. It is not for the same reason as above. Okay? Moreover, so but uh, for many things, okay, so at least in the case of, similarly, you can do the same, ask the same thing about Hermitian spaces also. Okay? I just gave examples of uh, of uh, uh, okay. So I mean, similar confusion can arise about Hermitian spaces also, but again, it is not the orthogonal complement. It's not the perp. Okay? So this is just so this just means okay. Okay, so and okay, so these are not the same, but of course they're isomorphic and they have the same dimension. Okay, so let's prove that statement. Proposition: dimension of V mod W is dimension of V minus dimension of W. Okay? Okay. So the way we will prove this proof is relatively easy. Okay. So okay, we're going to prove this only for finite dimensional vector spaces. Okay. The statement is true also for infinite dimensional vector spaces, but I don't know how much of Zorn's lemma, etc. you've done. So I don't want to. I don't want to confuse from this last class by writing things that are too general. Okay. So we will prove this for dimension V is finite. Okay. It is true in general also. So let W1 through WK be a basis of W. Okay, so we start with the basis of W. Then we can extend it to a basis of V. So we start with these things, first K of them, and the next, let's say n minus K, so we'll call it Vk plus 1 through Vn of V. So we have this uh, this this start with the basis of W, which we can extend to that of V. Okay, it is this argument that requires Zorn's lemma if you're not working in finite dimensional vector spaces. Okay, so I mean we don't need. I mean the assertion is true, but let's not worry about the proof. Okay, so extend to a basis. Okay, so now if we make a okay, so I claim the following: Vk plus 1 bar. Of course, W1 bar up to Wk bar are zero bar, right? Because their difference is already inside W. I mean, difference between Wi and 0 is already inside W. So Wi bar is 0 bar. So they are 0 vectors inside. I mean, they all give a 0 vector inside V bound W. It's the rest on which we place our hope, and that is what will work. Vn bar is a basis of V mod W. Okay? And the proposition will follow from the. Okay? If you assume the claim, okay? then dimension of V mod W is n minus k, which is dimension of V minus dimension of W, which is what we are assuming. Okay. So now what is left is to prove the claim. Proof of claim. So we're saying that some set of vectors is a basis. So there are two things to check. Everything in V mod W can be written using these vectors, and these are linearly independent. So let's make the two assertions. One, Vk plus 1 bar to Vn bar span V mod W. That's the first thing to reach. I mean, this and the other thing. Okay. So take an arbitrary vector in V mod W. Okay. So let V bar be inside V mod W. So be any vector. So I mean, more precisely, let V be inside V and consider V bar. So more precisely, let V be inside V and consider V bar inside. Okay. We want to show that there exists lambda 1 through lambda n minus, just call it lambda k plus 1 through lambda n inside F, such that n lambda I vi bar. So this we want. Okay. So this vi. Okay. So now, and what data do we have? We have that this is a part of a basis, and the remaining elements are inside. So there exist. Note that there exist some mu1 through mu n inside F, such that V is some mu I wi, I goes from 1 through k, plus mu I vi, I goes from k plus 1 through n. Okay, so this we have. Okay. Since this is a basis, W1 through and I mean W1 through W1 through Vn is a basis of V. So this implies that now we are applying the, I mean, when you're taking cosets, we're just applying a group homomorph, I mean, linear transformation. This implies that V bar is okay. But this is 0. We just observe that since Wi minus 0 is already inside. This is a 0 bar, okay, inside. So this V bar can be written using Vk plus 1 bar through Vn bar. Okay, so these things form, these things span the set. Okay. So now we check that they are linearly independent. Okay. So now suppose that there is a relation among them. So so let alpha 1, alpha k plus 1 through alpha n be inside F, be such that alpha I vi bar, I goes from k plus 1 through n is 0. 0 bar in V mod W. So what does this mean? This means that, okay, if you look at alpha, some alpha I vi, So this, when you're putting the bar, is just to say that when you are applying the natural linear transformation from V to V mod W, we get 0, right? So in other words, this is inside W. That's exactly, I mean, the things that go to 0 are exactly those that are inside W. Okay. So, but okay. Therefore, there exists, okay, alpha 1 to alpha k in F such that alpha I Wi equals, I mean, this is for I goes from, okay, maybe so you're expressing an element of W using these vectors. Okay? Therefore, that itself can be written in terms of W1 through Wk. And so then we rearrange terms and we get a relation like this. But this is a basis. So this means that alpha I is 0 for all 1 less than I less than n, which is what we wanted to prove. So this proves the claim that the image of, I mean, you start, so remember, it's not a basis for, it's not a basis of, it's not any basis for W. Okay? We have, it's not any basis for V. We have to start with the basis for V, for W, extend it to a basis for V, and the image of the things that are in the extension, okay, that are outside things, they are linearly independent. And that's, so that's exactly what what we have here. So, so this proves that the dimension of the subspace and the dimension of the quotient space are complementary to each other. I mean, inside the dimension of V, I mean, they add up and give a dimension. So this is a, so this again, one can still, but the same thing is also true for V mod W. Okay? I mean, for W perp. Okay? So W perp also has the same dimension as dimension of V, but as I said, this is not, they're isomorphic as vector spaces, but they're not the same vector space. One is a subspace, the other one is not a subspace. So another reason why we often have to worry about the quotient space and not, okay? So another difference between looking for orthogonal complements and quotient spaces, okay, is that uh, the definition of quotient spaces works in all situations, okay, while that of orthogonal complement works only for Euclidean or Hermitian spaces. Okay? I mean, you need a positive definite form to talk about an orthogonal complement. Otherwise, W perp may intersect W, right? Non-trivially. Okay? Works only when we have a positive definite form. Okay? Symmetric or Hermitian. Okay? I mean, it is. I mean, I don't want to. Either one of those things in the appropriate context. Okay? So especially if you're working, but applications. I mean, if you're working over a finite field, which you may not have seen, but you will see, okay? Or even over fields in which there is no natural notion. I mean, when you're working with a vector space where there's no natural notion of positive elements. See, in order to talk about positive definite, so you need to have an idea of what are positive elements, right? So, but if you're taking a field that's not real, or it's not easy to figure out what that, I mean, how to define positive definite in that case, okay? Especially if you're working on a finite field, for example. Okay? So, okay, so therefore, so I mean, this is somewhat more mean, it's a first of all, it's a different concept, but this things there's something work that doesn't. I mean, that only looks at the vector space structure without additional structure like an inner product. Okay? I mean, a positive definite form. So that's one thing that you should not confuse between these two things. I'm emphasizing this because it's easy to confuse them, but they're not the same. So I want to make one proposition, which I will just only. I mean, it's similar to the group case, so I will not. Uh, I mean, I will try to be quick about saying that. Okay, so let T from V to W be a linear transformation. Okay. Let V1 be inside the kernel of T be a subspace. So then, okay, then there are. I mean, okay, then there exists a unique. This means unique linear transformation. Okay. Let me just call it T bar from V mod V1 to W, such that. Okay. So the diagram that we should keep in mind is the given map is V to W. Okay. Then there is a natural map to the quotient space. Let's call it pi. And this is what we are saying. There is T bar. Okay. And so T of V such that for all V inside V, T of V is same thing as T bar composed with pi of V. In other words, that is T equals the composite of T bar with pi. T bar, sorry, pi followed by T bar. The existence and uniqueness is it's sort of similar to okay. So what we need to prove is that. Okay, so I'll just sketch, define T bar of some V bar to be T of V. This is exactly what we did in groups also. And then check that this works. Okay. Moreover, so T bar is also a linear transformation. We can ask what is its kernel. Okay, its image is same as image of T. Okay. But what is its kernel? Well, kernel is kernel of T mod V1. Image of T bar is image of T. Kernel of T is kernel of T bar is kernel of T. This is a subspace of V. V1 is a further subspace of kernel of T. So we can talk about the quotient space, and this is V1. Okay. So therefore, T bar is injective if and only if V1 is kernel of T, because they know. So this is V1 is kernel of T, and in which case we get the isomorphism. So therefore, then in which case okay, T bar gives an isomorphism from V mod kernel of T to image of T. So all of these things are similar to the group picture that we've done. Okay, so therefore, in some sense, this is an appropriate point to look at quotient spaces. Okay. These are not, I mean, thinking like these is not something new. Okay, so this is okay. So now, okay, so I want to end this thing by reproving the following theorem. So let V be a complex vector space and T a linear operator on V. Okay, so then we proved that there is a basis for V with respect to which T is a diagonal matrix. Okay? Then there exists a basis of V with respect to which T is given by a diagonal matrix. Okay. And the place, and we observed this earlier also, the place where we use that it is a complex vector space is to use that there is an eigenvalue in that field itself, okay, and therefore also an eigenvector. So that's what we used. Okay. So the same generalities that we talked about there will also work here. But let me just prove this. So we proved this again by induction on n, okay, but in somewhat complicated calculations. Okay. But here, once we discuss quotient spaces, this becomes a very natural proof. I mean, at least more natural than what, at least more natural in my opinion than the proof that we did earlier. Okay. So this is a proof. Okay. So let lambda in C be an eigenvalue, and V1 an eigenvector for lambda with eigenvalue lambda, eigenvalue of T, eigenvalue lambda, eigenvector of T. Okay. Let W be the span of V1, the span of V1. Okay. So now, of course, the statement is true if dimension, if n is 1, because if n is 1, there is it's just a 1 by 1 matrix which is diagonal. Right? So we may assume, so without loss of generality, so it is true. Okay, maybe I should have started out writing this properly. Proof. Inductor on n. And if n is true, if n is 1, then this is okay because it's just a 1 by 1 matrix and it is diagonal. Okay. Okay. So assume n is greater than 1 and that the proposition is true.
Yeah, sir.
Yes.
So I don't understand how it can always be a diagonal matrix.
How we prove this? Complex. Sorry, it's a diagonal. So I'm sorry. Triangular. I'm sorry. Thank you. I I was thinking triangular, but I wrote diagonal. No. I mean, whatever I wrote is incorrect. I mean, there are Jordan blocks, right, which are not diagonal. So yeah, sorry, I meant triangular matrix.
Mm.
Is that okay? Yeah. Thank you. Yeah. Okay. Yeah. So inductor on n, if n is 1, it's okay. 1 by 1 matrix is triangular. Okay. So assume that n is now greater than 1 and that the proposition holds for all vector spaces of dimension strictly less than n. So now we want to prove that it holds for all vector spaces of dimension n. I mean, as I explained, although we say although it might give us the impression that we have fixed a vector space and trying to argue for that thing, no, that is not what we are saying. We are making a statement about positive integers. That for every vector space, I mean, for every positive integer n and for every complex vector space v of dimension n, some blah holds. So the assertion, at least we are recasting the assertion as a statement about positive integers, and therefore we can use induction. Okay, so this I explained it once. Okay, it may be, I mean, we never write it like this. We will just say inductor on dimension. Okay, so it may give the impression that we have fixed the vector space and trying to argue about that. That's not the case. Okay, so then dimension of v mod w is n minus 1. Okay, this is one dimension. Okay, so therefore, okay, there exists a basis for v mod w with respect to which the action of t on that on the okay. So now, okay, so the key point that we need to keep in mind is that t induces linear transformation on v mod w. Since, so you should check this part, since t of w is inside w for all w inside w. It's not true in general. If T is if you take some random subspace V W inside V and ask this question, it will not work. Because TW is inside W, it induces the map from T from V to V gives a map from T from V mod W to V mod W. Okay? I mean, it is important that this. Okay, so this you should check. Okay. Okay. Therefore, there is a base of V. So let me call this thing T1. Linear transformation T1, with respect to which T1 is um, is given by a triangular matrix. Okay. Okay. So this is what we have by induction. But what does the basis of, I mean, what does vectors of V mod W look like? They look like the equivalence classes of elements of V. Right? So you can write them as some V2 bar up to Vn bar. Okay. So let so the point is that the vectors actually come from V. It is just their images inside V mod W that form a basis. So I want to V2 through Vn inside V be such that V2 bar up to Vn bar is this basis. Basis of uh, of V mod W. This with respect to which, okay. So this is what we have. Okay. Okay, maybe I should just write this. Okay. The thing is T1 of V bar is T of V bar. That is that's T1. So check this. I mean, given this explicit statement, you should be able to check that this thing works because TW is inside W. Okay. So this is the if V2 through V and V are such that this is the basis for V mod W. So now we take V1 through Vn. So what do we know about T of? So then, okay, for okay, so we want to say that it is triangular. Okay, so let us say we have said that it is upper triangular. Okay, so T of so T1 of Vi bar for all I greater than or equal to 2 Vi bar is in the span of V2 bar up to Vn bar Vi bar. Okay, that's what we mean by saying it's so this is upper triangular. Okay, right? T1 of this thing is inside here, right? Okay. I mean, you don't need the basis vectors that come after it to write that T of. So, or equivalently, there exists lambda 2 through lambda I inside F such that T of Vi minus lambda I lambda j Vj, j goes from 2 to I, is inside W. Okay. So we are expressing T1 of Vi bar as a C linear combination of V2 bar through Vi bar. Okay. Now look at the same relation without the bar. Okay. So that will just say that the difference must lie inside W, which is the one that went to 0. Okay. So therefore, this is true for every one of those things. So therefore, with respect to V1 up to Vn, T is triangle. That is. I mean, I am not saying that this proof is simpler. I mean, conceptually, you have to digest the idea of a quotient space, make this proof, etc. But I mean, I think this is it has slightly better conceptual clarity than the other sort of computational proof that we did. Essentially, maybe the second week or something. So this is actually, it was when I was trying to prove that I realized that the book does not discuss quotient spaces. Then I checked Professor Ramdas' notes, and there was no mention of quotient. I mean, there might be, but I don't think I forget if there was a mention. But I got the impression that it has not been discussed. So I just went with the proof in the book itself. But then then I realized that probably the reason why the book didn't discuss is that it had not discussed groups or quotient groups, etc. by then. So I think it is a good time now to understand, to think about quotient vector spaces, and at least revisit one of the earlier theorems, which I think conceptually is much clearer if one uses the idea of quotient spaces. I'm not saying that the proof as such is simpler, because there's a certain logical effort to digest what a quotient space is and to check the statement, etc. And for example, proving such things like this. But these are sort of typical things that one does with when one has to work in some abstract linear vector spaces, which does not have any inner product spaces, etc. So I'll stop here. Okay, so this is, as I said, this is the last lecture, and so I will. So since your exam is in person, I will see you on the exam day.
Thank you, sir.
Thank you.
I'll stop here.
Thank you, sir.